Today's lesson is going to revolve around solving right triangles. In class, we've prepped this a little bit beforehand, but the idea behind solving right triangles is that you're going to find the measurements of all its sides, if it's a triangle, all three sides, and all three angles. What they'll need to do is they'll need to probably tell you that this is going to happen in a right triangle. Then they can either give you two side lengths, or they can give you one side length and a measure of one of the acute angles. We'll make use of three things. We'll talk about using the Pythagorean theorem. We'll talk about using the triangle sum theorem. And thirdly, we'll talk about using the trig ratios. They could either be those or just the regular or the inverse trig ratios. So we'll have to probably make sure we understand the idea of SOHCAHTOA ahead of time. Here's the idea of the inverse trig ratios. Most places they're called inverse tangent. You'll also see them every so often talked about as arctan, arcsine, and sometimes you'll see arc cosine. But generally speaking, we'll talk about these being the inverse tangent, the inverse sine, and the inverse cosine. The idea is that if you're given two side lengths like these ratios right here, you can actually use the inverse of the tangent function in order to find the angle. It is read the inverse of the tangent of x, something like that. Let's try this out really fast. If we're given two sides of this triangle in order to find MN, we'll call this H for the hypotenuse. What we do is we would actually use the Pythagorean theorem. When we set this up, we would just say that's going to be 15 squared plus 7 squared is going to equal H squared. That would give us 274 equals H squared, or H equals approximately to the nearest tenth 16.6. This is a rounded number, so what I want to do is I want to try to avoid using this number at all costs. If I can just use the numbers that are given to me, it'll be a lot more effective. I will not be introducing error or rounding into my problem, so I'll be able to get some much more exact answers. If I was trying to find n, from n, this is the opposite side, this is the adjacent side. So which trig function deals with opposite and adjacent? That's going to be the tangent function. So I'll say the tangent of n equals the opposite over the adjacent. Or in other words, n is going to equal the tangent inverse of 7 over 15. Sometimes you'll see the measure of angle n written that way. Sometimes you'll just see n. In this case, n is going to equal, I think it's going to be 25.0 degrees. At that point, if we wanted to, if this is 25 degrees, we could then use the triangle sum theorem to say this is going to be 65 degrees. And that solves our triangle for us. We know all three sides, we know all three angles. Similarly, what we could do is if we're going to use this, we could say that A is going to equal the sine inverse of 0.36. What that would do for us is it would give us the measure of angle A to be 21.1 degrees. Similarly, this would be the tangent inverse of 0.8. That would give us that A would equal 38.7 degrees. Down below here, if we concentrate on angle A, this is our hypotenuse, this is our adjacent side. The trig function that deals with adjacent and hypotenuse is the cosine, so the cosine of A is going to equal 6 over 23, or in other words, A equals the cosine inverse of 6 over 23. That gives me the measure of angle A to the nearest tenth is 74.9 degrees. This example over here, it should be pretty similar. The idea here is this is just going to be the opposite side, and this is going to be the hypotenuse. So we'll be using the sine of A equals 12 over 60. If we want, we can simplify that fraction one step, but it still turns out to be the same, the sine inverse of 1/5, which should give us that A equals approximately 11.5 degrees. Next, we're going to be solving the triangles, and this is each problem is a little bit different. Each triangle is a little bit different. The idea with this one is that we're given one angle and the 90-degree angle, so maybe the first thing to do is just to use a triangle sum theorem to come up with this being 53 degrees. Again, if I mess this up and I would say this is 43 degrees, I do not want to use this angle, because if I mess it up and I just say the wrong number, like 43 degrees, then I use it to find the other two sides, I'm really putting myself out that I'm going to miss two of the three components. I'm going to give these temporary variables, say these are x and y. So based on 37 degrees is going to be my opposite side. This is my adjacent side. This is, again, my hypotenuse. So I could say something like based on r, if I was just going to try solving for y, that's the opposite of the hypotenuse. So the sine of 37 degrees equals my y over 22. or y equals 22 times the sine of 37 degrees. Y would then be approximately 13.2. This is a rounded number. I could use the Pythagorean theorem with 22 and 13.2, but I think it's going to be introducing error or introducing rounding to this, and since I would have to square stuff, most of the time you're not going to get the right answer back. Sometimes you will, rounding to the nearest tenth. Most books will require you to round to the nearest hundredth, which will definitely show a difference here. So what I'll do then is I'll ignore y over here, and I'll just concentrate based on this 37 degrees. I have my adjacent side, my hypotenuse, so that means I'm going to be dealing with the cosine function. So the cosine of 37 degrees equals the x over 22, or x equals 22 times the cosine of 37 degrees. That would mean x would equal 17.6 when I round to the nearest tenth. The second triangle, actually a different concept here. This one they gave us one side length and one acute angle. Over here they just give us two side lengths. So the very first step that I should use is I should probably use the Pythagorean theorem, saying that 11 squared plus 18 squared is going to equal, I'll just call this my hypotenuse squared. That would give me, let's see, 121 plus 324, so that's 445 equals h squared, or just my hypotenuse equals 21.1. Again, this is a rounded number, so I shouldn't use that the rest of the time when I'm calculating things. So then I'll just concentrate on n. The tangent of n will equal 11 over 18, because that's the opposite over the adjacent, or n equals the tangent inverse of 11/18. N equals approximately 31.4 degrees. And again, some books will write this as the measure of angle n. At that point, I could use the, I'm sorry, there's no angle m that I need to find. Angle P here. I could use the triangle sum theorem to say this is 90 degrees, plus over here this is 31.4 degrees. This should give me 58.6 degrees in the end. Otherwise, I could just use the tangent function one more time. Some other problems like this, they might give you some fractions in here. That's not a big deal. It still works the same way as this first one, where they give you an angle and a side length. This just turns out to be a fraction. Means probably we'll have to find these. They'll probably be fractions as well. This one gives us a radical, so not a bad idea to end with radicals, but it does tell us to round to the nearest tenth. So just treat this like it's a decimal, and this guy over here will probably be a decimal as well. Same concept here. We're just given a radical. Just makes it a little bit more complicated. Let's go to some story problems. This makes perfect use of the idea of the angle of elevation and angle of depression. What you have is you have some sort of Farquhar thing here going on, where you're jumping between buildings, whether it's free jumping or freestyling or just called pure crazy here. If someone was to jump from this building to the other building, I think it's a poor idea. But let's just take a look at some of the measurements that we'll be dealing with. The difference in these two building heights, this is 320, this is 200. So right away as I'm looking at this, there's going to be a 120-foot drop between the two buildings. Now it talks to me about my angle of depression being 50 degrees. So if you're staring straight out, that's 0 degrees. So I'm talking about looking down at an angle of 55 degrees. That's what puts 55 there. I'm going to be solving for x, the distance between the two buildings. I'm basically essentially drawing this triangle right here, just down below bigger. So what I'm dealing with is from the 55 degrees. This is my opposite side. This is my adjacent side. So I'll be looking at the tangent of 55 degrees equaling 120 over x. In other words, x would equal 120 divided by the tangent of 55 degrees. When we put that in our calculators, x is somewhere around 84 feet. So if someone was to jump from this building to the other building, not only do they have to go 120 feet down, they also have to go 84 feet over, and that's why I say that's crazy. Next, we're talking about the Uniform Federal Accessibility Standards. My mom is actually in a wheelchair, and so I think about this often when I think about trying to push her in her wheelchair up some sort of ramp. Sometimes this wasn't always in place. I can remember going to the zoo one time when I was younger, and this was definitely not the case. It was much steeper than 4.78 degrees, and that really led to a lot of problems, pushing and grunting and whatever else on my part. As a 10-year-old kid trying to push your grown adult mother in a wheelchair up a hill. Sometimes difficult. Not to say that she is difficult nowadays. I love my mother dearly, but it's sometimes a difficult process. The length of one ramp is 16 feet. The vertical rise is 14 inches. Estimate the ramp's horizontal distance and the ramp's angle. Does the ramp meet the uniform pieces? So I'll just put number 23 right here. Probably draw a picture here. It says the ramp length is actually 16 feet. It drops down 14 inches. Right away, just drawing this picture, I'm noticing a few problems. One problem is that the units are in inches and feet. Probably would do me some good to convert this into inches just by multiplying by 12. So 16 times 12 hopefully gives me 192 inches there. It says I want to find the horizontal distance, which would be x. So in this case, as I'm talking about this, I can just use a Pythagorean theorem using 192 squared is going to, wow, let me start this one over. 192 squared is going to be equal to 14 squared plus x squared. In this case, I would get x to be approximately 191.5 inches, almost as long as this piece here, just because we're dealing with it being much longer. In this case, I could also talk about the sine of theta being the opposite over the hypotenuse, equal to 14 over 192, or theta equaling the sine inverse of 14 over 192. What that gives us is that our angle of theta would then be 4.18 degrees. That's our angle, which definitely meets the standard, so I'm going to say yes. Part 2 here asks us, let me switch colors again. Part 2 says you want to build a ramp with a vertical rise of 6 inches. So this part here is 6 inches. You want to minimize the horizontal distance taken up by the ramp. So as we build this ramp, we want to minimize this. So our angle theta is probably going to be this 4.78 degrees, because if it's any bigger than that, if it's any less than that, we're actually going to have more horizontal distance. You want to minimize the distance taken, draw the sketch of it, and approximate the distances or the dimensions of your ramp. So if I was to try to figure out this horizontal length here, I would basically say the idea here is this is going to be the opposite over the hypotenuse, or the adjacent, I mean. So this would be the tangent of 4.78 would equal 6 over x. In inches, this means that x is equal to 6 divided by the tangent of 4.78. This is getting to be really sloppy handwriting. Or x equals somewhere around 71.75 inches, which is almost dead on with 6 feet. So that'd be the length of your ramp. You could then go through, if this is 6 feet, this is 6 inches, we could figure out what our hypotenuse is as well. Really like hot air balloons. I used to go to the River City Roundup in Omaha, Nebraska growing up. We get a good pancake breakfast, my dad and I. We get to hang out, and we get to watch all these hot air balloons take off in the morning. It was a really exciting process. I remember going to this several times as a kid. I always imagined how cool it would be to fly in a hot air balloon. It's kind of one of those things on my bucket list to do. What happens is you're in a hot air balloon and you're 600 feet in the air. Directly below you, I'll just call this point A, that's directly below you. So you're 600 feet directly above point A. When you look down at an angle of 30 degrees, so when you look straight across, that's 0 degrees. This is 30 degrees right here. 30 degrees, you'll see person B. Because this side is parallel to the ground, your straight out vision is parallel to the ground, this works as a transversal, meaning that these two angles are alternate interior angles. So we could also say this is 30 degrees. What I would do is I could probably solve for x, the distance between A and B, by making use of the idea that I had the 30 degree angle and the 600 feet. So I could say that this is the opposite, this is the adjacent, so I could say the tangent of 30 degrees is equal to 600 over x, or that x equals 600 divided by the tangent of 30 degrees. That gives me x equal to approximately 1,039 feet. In a very similar fashion, let me switch colors so this makes a little bit more sense. When you look straight out and you look at person C, you have an angle of depression of, again, 20 degrees, making this angle right here 20 degrees, meaning that I could set up yet another tangent of 20 degrees equals 600 over, let me just call this entire distance from A to C, let me call that whole distance y. We'll say that's y. So y would equal 600 divided by the tangent of 20 degrees, or y equals approximately 1,648 feet. That's number 26. How far are the two people apart? 1648 minus 1039. We're looking at 609 feet approximately. That's how far apart they are. You could also look at the game of golf, an angle of depression here from the tee box. I guess that's up here. The tee box to the green is 10 degrees, which is also 185 yards apart. With this triangle, it looks something like this. Here's our 10 degrees. Here's 185 yards. We're trying to figure out what this height of this drop-off is. How much higher is the tee? And it says around in the nearest yard. This is going to be our opposite side over here. This is our adjacent side, so we're going to use the tangent. We'll say the tangent of 10 degrees equals 8 over 185. H equals 185 times the tangent of 10 degrees. That gives us H equaling a really nice 32 yards. I almost wrote feet. Those are yards. Nice handwriting. That's awesome. 32 yards. Very similar process here. You're designing a ramp where the horizontal distance is twice as long as the vertical rise. So if I call this x, this is my vertical rise, my horizontal distance is going to be 2x. My horizontal distance is twice as long as my vertical rise. Vertical rise is x, horizontal distance is 2x. What happens then is if I want to try to figure out this angle, it doesn't really matter what numbers I put in here. If this is 10, this is just going to be 20. If this is 100, this is just going to be 200. It's always going to be double whatever that is. So when I talk about these two things, because I'm dealing with the opposite and the adjacent, it's going to be the tangent of theta equaling the opposite, which is x, over 2x. When I simplify this, this is the tangent of theta equals whatever it is, it's going to be 1/2. Whether I put in 100 or 1,000, 200 or 2,000, doesn't matter, it's still going to be 1/2. So when I deal this, this will be the tangent inverse of 1/2. That's a half. Holy smokes. And theta equals approximately 26.6 degrees. One thing I want you to notice is that each of these problems we've dealt with right triangles. This is right triangle trig. There's another example here dealing with a bridge. I want you to just take a look at this problem. It does not have a single right angle in it. Excuse me. No right angle in it. Wow, that was crazy. I love sneezing. No right angle in it. So actually there's a different idea that we would have to employ. That's called the law of sines. The law of sines. And this is for a different lesson actually. It's probably the easiest way to handle this. There's probably another really clever way of probably dividing this into some right triangles. But until you have the right triangles in here, you can't employ this concept. Even if you're given two angles, trying to find the third angle, you could definitely do that. But ended up trying to find any of the other sides. Doesn't really work unless you have right triangles. The same goes on here when we're given different pieces here, such as 40 degrees and 65 degrees. We're not really given a right triangle until maybe we make this a right triangle. I think the best way to solve this is, again, using something called the law of sines, which is really for another lesson. If you've seen the law of sines, try these two problems out. They're actually pretty good problems, but I wanted to point them out because they do not use right triangles, so we cannot employ the same techniques that we've been using.